Let's finish this off. So, as we take a look at the one you guys had to try on your own, we were dealing with sodium hydrogen sulfate, and we were told, and remember, this has to happen, you were told that you got a red solution when HMR was dropped into it. All right, well, that's methyl red, and when you take a look at methyl red, it is only red in pH solutions of 4.8 or less, which definitely places this as something acting acidic. All right, so we know we've got an acidic solution. When we take a look at a sodium hydrogen sulfate here, or sodium bisulfate, we have to decide, is it ionic or molecular? All right, there's the sodium ion. That's a dead giveaway that this is ionic, so it must dissociate first. All right, so it dissociates into sodium ions and the hydrogen sulfite ion. When we go through this dissociation, again, we see no evidence of the acidic or basic natures that we're looking for. In other words, no hydroxide and no hydronium appear. And so, with respect to that, we have to figure out which one of these two things could possibly go forward. And again, we see that group 1 metal of sodium ions, which cannot further react with water. So I kind of like dash crossed it out here to say it can't play. It must be the hydrogen sulfate ion. So therefore, it's the one that goes through hydrolysis with water in the ionization reaction to produce hydronium. So that means water has gained an extra hydrogen. So where did it come from? It came from this hydrogen sulfate ion to create the sulfate ion. And now we have an equation that explains the acidic nature given to us by the evidence. All right, we're going to go through a couple more. These ones are a little bit more tricky in some ways. Not really, though. And so if we take a look at number 8 here, we have calcium oxide, which is a metal oxide. And according to the evidence, calcium oxide always produces a basic solution. Well, we've already been told it has a metal. The metal is calcium. Therefore, this bad boy here has to be ionic. And so it must undergo its dissociation process first. And so we'll dissociate it. That will be into the calcium 2+ ion. And therefore, we get the oxide 2- ion in solution. All right, from here then, which one is the likely one that can undergo further hydrolysis or a secondary reaction, this time with water, in order to produce the basic solution that we see? Well, it can't be a group 2 metal. We've already said that those can't do this. So it must be the oxide ion. So we go forward, and so there's our oxide 2- ion. It must go through hydrolysis with a reaction with water in the ionization reaction to produce, hey, if this is a base, it must be OH- ions. All right, so there's your connection. All right, and so if water has turned into hydroxide, that hydrogen had to go somewhere. It went to the oxide ion, and lo and behold, you get a second hydroxide in solution. Okay, so you could simplify this, and you could say or to OH- if you wanted to clean up the equation a little bit. I'm happy with either. Both work. Okay, the next one, carbon dioxide. Hey, if I put carbon dioxide into solution, if I bubble it through water, it always produces an acidic solution. Okay, so I know I'm supposed to get hydronium out of this some way. As we take a look at carbon dioxide, and this is a non-metal oxide, we have another special case here that we're going to employ. Before we do that, we should figure out if it's ionic or molecular. Well, carbon dioxide we should recognize as 2 nonmetals, therefore molecular. So this is just going to go through hydrolysis or ionization right away. So this goes into a reaction with water. One thing that we had said, if you can recognize your nonmetal oxides like carbon dioxide, sulfur dioxide, and so on and so forth, it becomes a lot easier if you just double the water. Okay? And you'll see why in just a moment. If this is something that is acidic, all right, then I have to produce the hydronium ion. If I had just one water, I don't have enough hydrogen. So if I have 2 waters, all right, in this one, then I have an available hydrogen to go somewhere else. One of these waters has picked up an extra hydrogen, and so I have essentially an OH group that can go with my carbon dioxide, and so I create HCO3, 1 minus, and that'll be my other one. This is a little bit trickier just because of what we see happening. If I have to make H3O plus from water, all right, there were no extra H's until I had more water involved. So this is kind of like a little bit of a unique case. Just to simplify it for you, if you can recognize nonmetal oxides, and your nonmetal oxides, you add extra water to your reaction, you will have the available hydrogen to make hydronium, and you'll have the available hydrogen and oxygen, the remainder of water, to make whatever other ion you should have. Okay, so again, we're just looking for a proving step. One more to do. I'm going to have you guys ignore number 10. We would do it if we were in lab, and I would take some time to talk about how this is a very complex reaction. But working with aluminum nitrate, all the students would have predicted neutral. And when we go through, we find out it actually behaves differently, and we get an acidic reaction, yada, yada, yada. Don't worry about it from home, okay? Don't spend any time on number 10. Please ignore it. And I wouldn't even play with it. It's something that's quite complex, but is a good one to show if we can play with it in lab. One more to do. We're going to take a look at sodium nitrate, and here's a unique one. We haven't done this yet. According to the evidence, sodium nitrate always tests as neutral. Okay, let's see if we can prove why sodium nitrate is neutral. Here we have sodium and nitrate. You have a metal ion, you have a negative polyatomic ion. That must mean it's ionic, so please dissociate this one. As we go through the dissociation reaction first, all right, you can see that we have to produce an Na plus ion in solution, and we have to produce the nitrate ion in solution. Now, this could have things that potentially react with water later, so we should analyze it. But here we see a group 1 ion. Group 1 ions, I think, should be very clear with the number of examples we've gone through by now, cannot react with water. And so sodium is not potentially there to cause any sort of acidic or basic nature. We've also said group 2 ions don't work, and always nitrate stays in solution, so it cannot react with water. All right, this was one of our memorized things about the solubility chart. Nitrate is always soluble, so that means nitrate always stays in solution, and so nitrate doesn't really react with many things, and so it was the third thing on our little list from part 1 of the lessons when we looked at things that would not continue on in the reaction. So when sodium nitrate dissociates, you don't create any particles that can hydrolyze with water, and therefore no further reaction can go on. No hydroxide has been produced, no hydronium produced, and so you remain at a pH of 7. Okay, so hopefully that all makes sense to you guys now. All right, this is our finishing topic for Chapter 6. We will not go into 6.5. Again, doesn't hurt to read, but there will be no explicit questions on it on your upcoming test. Read, 248 to 253. There are additional examples in the textbook that you should be paying attention to. There are solved solutions in there that you should be paying attention to. It's a different presentation. It's always good to see multiple versions of the same idea. 251 and 253 have a few practice questions. Finish that off, and everything should be golden. Again, if you have any questions, make sure you're checking in with me, and I can certainly help you out. But I hope that these examples and that your trials between videos have worked out well. All right, good luck with everything, and yeah, we'll see you in the next chapter.